Buenos días a todos. Hoy tengo el gusto de poder presentaros a Lorenzo Bardella. Él es ingeniero de caminos y es profesor de la Universidad de Brescia. Se dedica a la simulación, micromecánica, homogenización, campos de deformaciones, demás cosas, y está ahora aquí porque está trabajando junto a Javier Segurado en una acción hispano-italiana, y bueno, pues nos van a contar acerca de su trabajo, y esto va a ser el principio de, espero, una larga colaboración. Yo no me puedo quedar, así que os hará los honores Javier Segurado, ya que le conoce bien, al final de la charla, así que cuando quieras, y muchas gracias.
Thank you very much. First of all, my apologies for not speaking Spanish, so I'll try my best English. If you don't like my English, just stop me and I'll switch to Italian. My Italian is good and I'm sure you'll understand it. Thank you very much for inviting me to give this talk. And yesterday I was kind of impressed by this beautiful place, all the laboratory facilities, they are really great. So I'm happy to be here. And I tried in this talk is about trying to phenomenologically model the size effects with strain gradient plasticity. And in particular, I try to say something about all the length scales parameters that one can put in the modeling. And I tried the simplest presentation, but if I'm not clear, please stop me and I'll try my best. But the first motivation, my very first motivation for starting this work was given to me by John Willis, who asked me to homogenize polycrystals in order to compute the effective properties and the size effects, something like a discussion, an analytical discussion of the Hall patch effect. And he already did with Norman Fleck for the case in which each grain is approximated by an isotropic model. So he asked me to do the crystal plasticity calculation, so I started working on strain gradient crystal plasticity. Oops, too much. Okay, let's start with this benchmark. This is a strip, a single crystal strip. It is compressed between two bodies in which this location cannot penetrate, and it is subjected to simple shear. Okay? So here I have put a couple of zip planes, and there are these blue edge dislocation. When you subject the strip to simple shear, these locations start moving on this slip plane, and they pile up on the border where they cannot penetrate. Okay? So the slip, each slip is gamma.
It's two-dimensional case.
C, yes. Sorry for C, yes. Yes. Two-dimensional case. So these location lines are just piercing this plane. So once you have the slip on each glide, you combine them in order to compute the plastic strain. And the plastic strain is given as the sum of the slip times this Schmid tensor that depend on the crystallographic details, the slip direction and the normal to the slip plane. Okay? And once you compute this plastic strain, you find something like this. And the plastic strain has to be zero close to the boundary, because there the dislocation just stop. And the point is that if H is quite big, you don't care about this boundary layer of plastic strain, because it's negligible in comparison to the dimension of the strip. And so standard plasticity works, and you just predict homogeneous plastic strain. Instead, in the size dimension between a few hundreds of nanometers and a few tens of micrometers, this process zone counts a lot, with the usual smaller being stronger. Okay, and this is too sensible. Okay, so I wish to predict size effects like this one. If I plot the uniform shear stress on the strip against the applied strain. As I go down with this dimension, I see the strain hardening increase. Okay, this is one size effect, and it depends on the length scale, which is related to this process zone. Okay, so let's imagine we just go down with the dimension and we see this slope of the hardening curve increasing. Another typical size effect is this one, is the strengthening. So this means that it depends on a different mechanism, and when you decrease the size, you see the yield stress increase, and there is no much change in the slope of the stress strain curve after the yield stress. More or less some approaches to plasticity. Standard plasticity is not able to reproduce any size effect. Of course, there are no length scales involved in the model. Can be isotropic or crystal plasticity. And the first easy approach to try to describe some size effect is the so-called low-order plasticity. Also, this can be isotropic or crystal plasticity, but you just put in a really, let me say, rude way some dependence on the gradient of the plastic strain just in the tangential modulus in order to predict some size effect. There are no higher order stresses or higher order boundary conditions. Instead, my talk is about the higher order strain gradient plasticity. Also, this one can be crystal or isotropic. And here we have non-standard boundary conditions, non-standard stresses, and so on. And the basis for this theory has been given by well-known scientists, Gertin, Fleck, Hutchinson, and so on. Okay, then even more detailed description is the strain gradient plasticity, in which you also have evolution equation for the dislocation densities, which is not the case of the theory I'm talking about. Then you are expert in discrete dislocation dynamics, okay, which is a much more detailed description, and you abandon the continuum description. This is discrete, and even for even more detailed description, you can go to the atomistic. Of course, as you go down with the size, you can perform more detailed analysis, but they are expensive. Let's go back a little bit on the notation. Just in this light brown, I copy the equation in symbolic notation instead of index notation. Okay, the strain is the total strain is as usual the symmetric part of the displacement gradient, and this displacement gradient is divided into an elastic part beta and a plastic part, which is the plastic distortion, and is obtained by combining again the glide, the slip on each system with this crystallographic unit tensor. Okay, and if you take the symmetric part of the plastic distortion, of course you have the plastic strain, and this becomes the Schmidt symmetric tensor. Okay. I talk about the deformation theory of crystal plasticity, not flow theory, because when I started this work, as I said earlier, my goal was an analytical homogenization, so no way to do it with the flow theory. Also, the deformation theory is quite a mess, but anyway, the first approach was deformation theory because it's much easier to deal with. And anyway, the most important thing is that this deformation theory is developed on the basis of the flow theory. So we always have a parallel with the flow theory that we can develop together with the deformation theory. Before talking about the strain gradient extension, I'd like to say something about the classical deformation theory of crystal plasticity. So no size effect involved, just classical stuff. You start by defining the straining potential, and in the straining potential there is the linear elastic energy, plus this plastics potential, which is a function of the slip vector, which is a vector that collects all the slip systems, all the slip available. And the strange thing with respect what we are usually accustomed to is that we define two independent kinematic variables, but independent just because of the stress conjugation, not because they are physically independent. Okay, so we associate a stress, the usual Cauchy stress, to the total strain, and also we associate a new stress to each plastic slip. I cannot. Perhaps I should use page down. Yes, and so this is what I said. This new stress S, there is an S for each glide, is conjugated to the plastic slip on that glide, and it turns out to be this difference between this stress H, which is a function of the slip in the model, and this tau, which is the resolved stress on the slip system you are considering. So is the Schmid stress. This one? No. Okay. Okay. Once you put this technology into the total potential energy, you just look for the minimum. So you write down the stationarity conditions, and what you obtain the usual divergence of the Cauchy stress equals 0 if you don't have body forces, but you have another equilibrium equation, which is this one. This new stress we have defined is just 0. And this means, this is an equilibrium equation, this means that we have this equality, which is the usual flow rule. Okay, the Schmid, the resolved shear stress must be equal to some function of the plasticity you have. And in the flow theory case, it's a little bit different, the definition of this stress, because it's not in terms of the actual plastic slips, but of course, usually you use the accumulated plasticity. Okay. But the field equations are exactly the same in the flow theory or in the deformation theory if written in terms of stresses. Then it's just a matter of defining the stresses. Okay. Now let's go to the strain gradient extension. And first, I'd like to introduce the most important kinematic variable in order to extend the model to the strain gradient case, which is the nice tensor. And what you try to copy what these locations do, what this discrete dislocation does into a real crystal. So here you have an edge dislocation and a screw dislocation, and this is the usual business in order to obtain the Burger's vector due to this dislocation. Okay, if you divide the displacement, the gradient of the displacement into the elastic and plastic part, you know that the plastic part, the plastic distortion, usually, if you integrate it in a closed line, it doesn't give 0 because it's not compatible in general, but it gives a net Burger's vector. And this is, in this picture, we have a few edge dislocations, and if you do this operation, all the dislocations with a different sign just compensate, and finally in the Burger's vector you have only the surplus of dislocations of the same sign, so in this case only the red one, and these are the so-called geometrically necessary dislocations. And so then if you apply the Stokes theorem, you pass to the surface integral, and you define the curl of the plastic distortion as the nice tensor. So the first index in nice tensor is related to the net Burger's vector. The second index is, this is a second order tensor, of course, is related to the line dislocation line direction. Okay, you got to compute this net Burgers vector in this way. And so a nice dislocation density tensor is a representation of G and Ds. As I said, the first index is related to the Burgers vector, the second one is related to the direction of the dislocations you are accounting in doing this on the surface S, in doing this integral. So we'll skip, of course, all these mathematical details, but what I'd like to say is that if you take this definition of nice tensor and you substitute the definition of plastic distortion, you can write nice tensor in terms of slip gradients and some crystallographic details. These are all the unit vectors that define the crystallography you are considering. The main thing, why we do this, because we can recognize that the component of the slip gradient on the slip direction is a pure edge dislocation, whereas the component of the slip gradient on the transverse direction in the slip plane is a pure screw dislocation. Why this? Let's see if we can. Okay, if we consider an edge dislocation, look at the first term of this definition, this expression for nice tensor. The edge dislocation has a gradient along the slip direction, M. Okay, so the gradient has to be projected onto this direction, and the Burgers tensor is directed as M, as usual. The line, edge dislocation line, is exactly T. So this first term is a kind of representation of pure edge dislocation. The same. Sorry, I did something wrong. Okay, the same happens with screw dislocation. Okay, in the case of screw dislocation, both the dislocation line and the Burgers vector are directed as M, and the gradient is in the transverse direction. Okay. So we want to use this nice tensor in order to extend the model that we have seen earlier. So we take the strain potential and we add the function of nice tensor, and we also add something else. We'll see in a second what this is. So we have the usual standard variables to which we want to conjugate some stresses. We have nice dislocation density tensor, and we have this matrix in which we collect all the components of the slip gradient. So the first two are dislocation densities, as we have seen. The third one is just an extension of notation, is the projection of the slip gradient on the normal to the slip plane. We just want to see how these affect the behavior. So what is this function? D alpha, D of alpha, is the defect energy. It has been defined earlier by Morton Gertin, and this is an energetic term. So if you write the flow theory, this is an addition to the free energy. So also in the flow theory, we still have here total value of the nice tensor. And what's this for? If you recall this picture, I mean, with the defect energy, you try to account the singularity in the Cauchy stress due to the dislocation that you have in your material. And so this is an energetic term. And since you account only for G and Ds, geometrically necessary dislocation, this means that if you are here and you are judging the effects of this dislocation, you see only the effect of the red dislocation. The other ones just compensate. Okay? So this is related to long-range effects. The back stress should be energetic, something like that. This other term instead try to account for the dissipation due to dislocation motions, so the whole population of dislocations, and this is completely phenomenological. Okay? Here I wrote down dots because I remember that this part in the flow theory is a dissipative part, so the stresses comes from some plastic potential, if you like. It's better perhaps in the flow theory call it some hardening function in which the main variables are rate of plastic measures, not total plastic measures. And the expectation is that this could model the strengthening. Okay? So after you have extended the classical theory in this way, you just run the usual technology. So you define for each of these independent kinematic variable, you define the stresses. There is the usual two stresses we have seen earlier for the classical theory, okay? And you define also the defect stress, which is dependent on the defect energy, and this has been defined. The transpose of this stress is what Gertin called the defect stress. And then there are these dissipative stresses, okay, conjugated to all these projection of the plastic slip gradients. Again, okay. Another non-standard stress that is useful to define is the microstress. And in order to define the microstress, you just conjugate this stress to the gradient of the plastic slip, in which you also consider the dependence of alpha and rho on the plastic slip. This is useful because you see it's a combination of the defect stress and the dissipative stresses. This is useful because it comes out in the higher order boundary condition. So beside the standard boundary conditions, you have these non-standard boundary conditions. You can do something more general, but from the physical viewpoint, we just consider that when this location cannot penetrate the boundary, you just set that the plastic slip, each plastic slip must be 0. When instead you know that this location can leave the body and make a step, you just say that the microstress, this higher order traction due to the microstress is 0. Then if you put all this stuff into the total potential energy, you find the minimum, and formally you find the equilibrium equations. And with respect to the classical case, we have this term, the divergence of the microstress, which enters the higher order equilibrium equation. So you have the standard divergence of Cauchy stress equals 0, and plus this one, which is the modified Schmid law. Okay, without the microstress, we have the usual stuff. With the microstress, we have this kind of complicated. If you replace the definition of all the stresses here, you obtain a very complicated partial differential equation system. Okay, and here you have the symbolic notation. Okay, this is exactly the same in the flow theory counterpart. The only thing that changes is the definition of the stresses, but the structure is exactly the same. So the great advantage of the total potential energy is that you have a minimum principle if you choose appropriately the plastic potential and the defect energy, and this principle together with its complementary function allows very easy calculations for simple boundary value problems. You just use RITS directly without any need to implement the model into finite elements, which is very complicated. So just a very simple choice for the defect energy. This has been earlier proposed by Gertin, just a quadratic form, very easy. For sure this is convex. And there are many other possibilities. One of them appeared on the JMPS in 2007, is this homogeneous of degree 1 defect energy. there are many works. I'm late? No? There are many works now that in which they try to find appropriate form of the defect energy. And they usually use gamma convergence just to make an average among these locations. You just choose simple problems. And I think one of the most important way to make this model better is just understand which should be the best form for the defect energy, which is not easy at all. And I hope that our collaboration with discrete dislocation simulations will help in understand something more about this. The plastic potential is even worse because it's completely phenomenological. And here I have tried a kind of complicated extension. Oh, sorry, I haven't said an important thing. Of course, once you define the defect energy, because of dimensional consistency, you got to put some length scale. Okay, mu is the shear modulus. Since alpha has the dimension 1 over a length, okay, to have an energy density, you got to put a length scale. And this length scale, if things would work, should be more or less the dimension of the boundary layer of plastic strains where dislocations pile up or something like that. So in that case, I have defined the defect energy in such a way as to have just one length scale. The plastic potential instead is much more complicated. And this is due to the fact that it's completely phenomenological. It's just a rude extension of the standard Mises plasticity for crystals. And so you take this power law, and which is standard in the deformation theory context, and we try to see each of the projection of the slip gradient, how it affects the description of the size effects by defining one different length scale for each of these projections. Okay. Usually P is equal to 2, but in my opinion there are no tough arguments to say that P should be equal to 2, besides that is much better for analysis. Okay? And so I tried these different values of P, and actually finally I concluded 2 is good, because it's really just a lot of complication for earning almost nothing in the description capability. And the interesting thing is that if you choose this length scale equal to 0, you have a model which is just dependent on dislocation densities, which is good from the physical viewpoint, because this becomes just dependent on dislocation densities, and of course the defect energy through nice tensor is just dependent on dislocation densities. I'd like also to say that here we have neglected latent hardening. You can add it, but it's even more complicated. And in this model we have an interaction which is natural, and I like it a lot, among different slip systems, and is due to the fact that this defect energy through nice tensor couples all the dislocation densities on various slip systems. Okay, let's go back to the simple shear, the benchmark, and I have run a lot of analysis with a lot of different crystallographies to see how it works. So we have big couples of symmetrically oriented slip systems. So that means that if I have this one, I have also that one in each material point. And in order to trigger inhomogeneities, which is fundamental to have gradient and to see a size effect, we must say that on these borders dislocations cannot penetrate. So our higher order boundary, non-standard boundary condition is just to fix 0 plastic slip up and down. And for instance, this is, here we look just at the effect of the energetic length scale, so nice tensor, and which is the guy who should rule the thickness of the boundary layer of plastic strain. Okay? So I plot the plastic strain. This is the normalized coordinate. This is the middle of the strip, and this is the border. And here there are two cases of the exponential parameter in the power law. So the so-called perfect plasticity case, which is not actually perfect plasticity because there is the gradient term, so you don't have a plateau. And the linear case is the maximum value of that one could put for n. And you see, if you change the dimension and you keep fix L, you see that for each value of this small r, which is this ratio, you have a completely different thickness of the boundary layers. So it changes a lot. And instead, if you keep this ratio constant and you look at the effect of dissipative length scales, in this case, all of them are taken the same value for all of them. You see, you change this ratio and nothing changes for the boundary thickness, which is very good because that's what this model is built for. Again, we are not going to look at all these curves in details, but the point is that all these examples are for just one couple of symmetric slip systems, and this is fundamental, unfortunately, because things don't work so well if you change the crystallography, if you have more slip systems, and this is the main result of all these simulations I've done. And so for one couple of slip systems, if you neglect the dissipative strain gradient extension, you see that it works exactly as we wanted. So you change this ratio and you see a variation of strain hardening without any change, almost any change in the yield stress. On the contrary, you keep this energetic length scale fixed, you change the dissipative length scale and you have a strengthening. You see that the variation of strain hardening is almost nothing. So everything seems to work. And another curiosity, here I keep fixed all the length scales and I just change the exponent in the power law of the plastic potential. Also in this case, almost nothing changes for the thickness of the boundary layers. So this is good. The point is that I have time. So I move after the conclusion because I was afraid not to be able to stay. So I'll show you some other plot. For instance, let's take this one. In this case, we have two symmetric couples of slip systems. Okay, B is equal to 2. And you see, things don't work. This is n equals 0.2 is kind of realistic, is almost kind of small, so is almost the perfect plasticity case. And see, here I change a lot of parameters. In the previous plots, P was always equal to 2. Here I try different parameters, and I try different things, different combination. The only thing that I like to tell you is that you change a lot the energetic length scales, and unfortunately the strain hardening doesn't change almost at all. Okay, it's always strengthening. So the point is that if you want to have this size effect, the strengthening, if you put some dissipative extension, is always there. The point is, in my opinion, trying to understand how we can have some piece of the model that can always be related to strain hardening variation. And doesn't seem to be very easy. And I'll finish with this in trying to explain you this plot. that I like a lot when I found it. It took to me a while to understand why I had the results, so when I could understand it, I was happy. So this is the comparison between two different crystallography. Okay, B equal 1 is just 60 degrees inclined couple of this slip system. B equal 2 is this one plus a 45 degrees inclined slip system. The point is that on the 45 degrees inclined slip system, the Schmid stress is 0 under this condition, because the Schmid factor is 0. Okay, and so I would expect that nothing should change if I add this slip system. And in fact, if you have not too small and not too small strip, you see the curves coincide of the two crystallographies. But once you go down in dimension, what happens is the coupling in the defect energy that I was told you about earlier. And the higher order equation couples all the dislocation densities through the nice tensor. So it happens that in the higher order equilibrium equation on the 45 inclined slip system, you have a term due to the dislocations on the other slips. So what happens is that due to this defect stress, this is a defect stress, and some dislocation start moving also on the 45 inclined slip system. And this is good because this is what Javier could model with this discrete dislocation plasticity, because the inhomogeneities of his Cauchy stress for sure sooner or later can trigger some dislocation moving on this 45 degrees inclined slip system. So I go back to the conclusion. The conclusion was that for what concerns the plastic potential, this is the main variable entering the plastic potential. I think it's wise to take P equal to 2. This P norm should be the easiest one. And probably it's also a good idea to throw this term away so that we have a model just dependent on dislocation densities. And the main point, as I already said, is that the size effect due to the defect energy is difficult to predict. We don't know whether it is strengthening or strain hardening or whatever. Open issues a lot. We should find the appropriate form for this strain potential which extend the classical theory. And one interesting issue to me is the understanding of the higher order boundary conditions at the internal grain boundaries in polycrystal. Of course, I should sooner or later implement, I should do it within our project, the flow theory into finite element of this model, and so that we could perhaps compare for general boundary value problems this model with the dislocation dynamic technique, and then sooner or later perhaps I'll homogenize polycrystals. But I hope. Thank you very much. That's it.
So, if somebody wants to ask something, we have time enough.
It was a very nice talk, very clear, extremely clear. I really appreciate it.
Thank you very much.
A question I was giving about, could you implement other boundary conditions just in the simple strip we are dealing with, in which you have the dislocations can partially leave the boundary?
Yes. Yes. The mathematics says that you have just to put a value for the plastic slips where you have a kinematic condition, or put a value of the higher order traction where you have a static higher order boundary condition. A very recent work of Castrense Polizzotto, an Italian from Palermo. I like him because he is almost 80 and he keeps working and publishing, and it's unbelievable. Anyway, He runs some analysis similar to this one, and but on the top of the strip he has an interface, so you can play with the boundary condition and see. Also on the boundary condition you can put some energetic effect, some dissipative effect, so you can play with this location that can be absorbed into the green boundary, or that can be sooner or later promoted, the dislocation of the pile-up on the other body.
Yeah, the reason I'm asking is that we have seen recently, Javier and I just thinking some results, the enormous effect of boundary conditions on strengthening and size effects. And basically,
It's fundamental.
I mean, it looks like that you just change the boundary conditions slightly and the whole picture changes automatically because of the pattern of dislocation change.
Yes.
And I guess you can get a lot of results just changing the boundary conditions, trying to understand
This effect is even more important in the continuum modeling, because in your modeling, the dislocation dynamics, anyway, you have some other sources of size effect as obstacles or whatever. Here, the only thing you have in order to trigger inhomogeneities is the boundary conditions. They are absolutely fundamental. And a nice, with crystal plasticity, a main problem in polycrystals is that if you try to say something about the boundary conditions on the grain boundary, the problem is that the heterogeneities is due to misorientation. So if I label a slip in one grain as 1, the slip system 1 in the other grain has nothing to do with this one. So you cannot say gamma 1 is equal to gamma 1, that means nothing. So it's kind of, it's really, you can overcome this problem if you put some constitutive model for the grain boundaries, but so far what I've seen is not based on clear physics to me. So
you have two different things to account the size effect. One is the effect energy, the other is the potential. So you have two different nature of length scale. One is the small L, and the other one are the different L's that you multiply to the densities. Do they have a different physical nature?
Should be, because the small L that related to the effect energy should be related to the process zone where dislocation pile-ups. And because there you have a high density of geometrically necessary dislocation. Instead, the capital as the dissipative ones should be related to short interaction and motion. So it's completely, they are very difficult I mean, from the continuum viewpoint, finding a nice variable to express this dissipation is so far totally obscure. I mean, we just put a gradient.
So in theory, if you find correct values of both small L and big L, you should be able to reproduce any size effect on different problems that
yes, but first you should have the correct form of the energy, the strain potential, I mean, which is even.
How do you model within this framework size effects that come from dislocation and stabilization? I mean, in micromaterial when you have various mobility, sometimes, and this is one of the well-known theories, that sometimes you have a size effect because you have no dislocation. You have no dislocation sources available, or the dislocation exit rate from the crystal is higher than the dislocation.
The only way is to trigger somehow some strain homogeneity. So, for instance, if you take uniaxial tension, and if I say that these locations can exit the body everywhere, I have nothing. And if I wish to see some strain gradient, as you can see in dislocation dynamics, I should perhaps model a complicated problem in which I say that somewhere there is inside the body, so it's kind of complicated boundary value problems. I don't know how to do it now. I never thought the body. I should say that the plastic slip is 0 because there is an obstacle. But anyway, the general receipt is that you must somehow trigger a plastic strain gradient, and this is done with because of the boundary conditions, either the non-standard boundary conditions, or of course it's sufficient to have standard boundary. Of course, if you have concentrated load, you are okay anyway.
Yes, the fundamental question, I guess, is that sometimes there are size effects that may be, whose origin may not be strain gradients, and they may be very relevant, and then just with an strain gradient plasticity theory, you will never be able just to pick them up, and then you will have to add something else in the continuous framework you are dealing with.
I completely agree.
And this is something that that is even more basic of the very interesting basic things you have said, just to find a physical meaning for this length scale and so on. But I guess this is something that
I think in these strain gradient extensions, if you don't go deeper in the detailed modeling by including evolution equations for these locations, which are based on dislocation mechanics. If you keep this continuum description, the only very clear and nice ingredient is that coming from nice things. The other stuff is phenomenological. On the other hand, also Mises is standard plasticity phenomenon. No one says nothing about the Mises potential. It works. So I think the perfect modeling is not to be reached in any case. It would be full and engineering who's looking for the model that can model everything. We are just, the point is understanding what can we model with this stuff.
Yeah, that's very important.
How do you pick your initial dislocation densities?
You don't have an initial condition on the dislocation density. You don't need it. It's just everything happens because you have gradients of plastic strain. You could, of course, if you implement this modeling to finite element, you could decide to start with some eigenstrains, plastic eigenstrains, or whatever.
Well, the reason why I'm asking this is in some theories of polycrystals, they say that the initial dislocation density is varying depending on the size of the grain.
Yeah.
And that may be responsible to some of the size effect that's observed. So some of these strain gradient plasticity theory based on dislocation density will have the strain hardening that will change depending on the length scale you're choosing. But the initial yield stress will change depending on the initial dislocation density that you're picking.
I agree with you. It should be like this. The problem is that it is similar to that I just discussed. It becomes more complicated if you consider a polycrystal because many reasons. First of all, the behavior of the grain boundaries, which is, for instance, in the modeling of John Willis of polycrystals with isotropic plasticity for each grain, the only fundamental ingredient is the behavior of the grain. So he has this, in my opinion, beautiful phenomenological model for there is just a potential that rules whether these locations can pass or not the grain boundary, and then provides a lot. It's a very rich description of size effects, but it's even at a level less detailed than this one. So it's not, as I said, it's not very easy from the mathematical viewpoint to put a crystal model into a polycrystal picture if you want to describe without completely phenomenological terms what happens to the boundary. And of course, if you have a polycrystal, any condition you give on your body, you always have strain gradients. So something happens in your model.
So
You know.
would that be correct to say that by comparison with this other kind of strain gradient theory, the evolution of dislocation density would trigger a difference into the hardening, whereas your part with a small L would trigger the initial yield stress?
It's the contrary.
The contrary?
Yes, it should be, but as I showed with complicated crystallography, it's not like that. The defect energy should rule the strain hardening, whereas the dissipative term should rule the level of the yield stress. So small L is there to rule the strain hardening, which increases when you decreases size, whereas the dissipative term should rule the strain. That's the picture.
Last question, Carlos.
I think it would be physical reason to assume that the effect energy being convex or anything of that kind.
No, it's just mathematical good reason. For instance, if I take that one homogeneous function, the Okumura term, I'm done with my nice simulations because I cannot compute the complementary function. There is a Fenker transform. So I really like strictly convex functions. Of course, if you once you have understood what to do with the deformation theory, you go to the flow theory, and then the flow theory has to be implemented in finite element. So you put whatever you think is better. But if I want to solve this problem, there is really a mathematical trick, because in the complementary approach, the function for this problem has a very nice form if you discretize it with risk for some value of the nonlinear exponent. And it's just low-level stuff. I mean, it's just a way to make Mathematica works. That's it. So, for instance, there is this recent work of Berdichevsky on thermodynamics and continuum mechanics. I hope the name of the journal is correct anyway. And he proposed the defect energy completely different. There is a very complicated logarithmic term. Then there are these friends of mine in Italy, these mathematicians, who did this gamma convergence technique, and they found as Okumura a one homogeneous function for the defect energy. The point is that one homogeneous for infinite density doesn't mean much more, because after a while you can store more geometrically necessary dislocation. So it's really anyway, something can be done in order to have a better defect energy. What's completely difficult is the plastic, the dissipative extension seems to be really tough.
Do you consider to have even a two-well potential or something like that? A two-well kind of something of that kind, instead of something like this?
That would be even worse probably, but I mean,
from physical reasons, could even be considered to have something of this?
I don't know. Do you have any suggestion?
No, I don't know. I think more from a theoretical point of view, you could find additional problems that I don't know whether will come in reality or not.
Okay. Mathematics allows us to play with many
No,
many
the thing is that there are things that in nature, for instance, in the case of how do we call laminations, which is not the case, this kind of structure that are with this wiggling, you can have.
I'm sorry, unfortunately, I don't know whether the defect energy with those two minima could be related to something. So I don't know.
Okay, so we would like to thank you very much again for the nice presentation and class you have given us. And he will be here until tomorrow, so if somebody wants to speak with him, he will be available.
And I'll be happy.
Thank you very much.